Hello everyone, today we are going to discuss about code converters. Code converter is one of the example of combination logic cycle. So generally code converters are used to convert one form of code into other form of code. Generally we are having four different types of codes like binary, BCD, gray and XS3. So here we can able to convert from one code to other code to exchange the values, how it's changing from one form of code into other form of code. So here we going to discuss what are the steps to be followed to convert from one code into other code. Then we going to discuss about two different examples. So the steps here, the first so determine the number of inputs and outputs. I mean while converting from one code into other code, for example we are converting from binary to gray. So how many bit binary code, how many bit gray code. So based on the number of bits we have to decide how many number of inputs are there and how many number of outputs are there. Based on that input and outputs we have to derive the truth table for the particular example. Then after that, after making a truth table, we have to find out the simplified Boolean expression for the particular code. Then after that, we have to implement the logic diagram. So these are the four steps should be followed for designing any code converter. First one we will see the example of BCD to XS3 code converter. So BCD means we know the number decimal number going to change from varying from 0 to 9. In terms of XS3, so it's normal form of binary number, so we can able to write the XS3 code from 0 to 15. So as a 4-bit number, 4-bit BCD number is changing from 0 to 9. So as a 4-bit XS3 code converter, we can write it from 0 to 15. So now here we can able to convert BCD to XS3 code conversion, as well as we can able to convert XS3 to BCD code conversion. So generally this code conversion performing for a 4-bit number. So here as I said earlier, so 4-bit number as a BCD number is varying from 0 to 9. As XS3 code converter, so just we going to add 3. XS3, the meaning is we have to add 3 with the available input number. So for example, suppose the input values 0010 is a given input value. So what is the XS3 number for this 2? Decimal value is called 2. So what is the XS3 value for this decimal value 2 means? So just we going to add 3. So 0011. So add 3 with that number. So we are getting as 0101. So it's nothing but the decimal equivalent for this one is 5. So just adding 3 with the given input number is called XS3 code converter. So here the first we are going to perform a 4-bit BCD to XS3 code conversion. So first step, so 4-bit number we know, so we are going to take a variables for that 4-bit. So we are taking as ABCD. For a BCD input, I am taking the variable name is ABCD. So for the XS3 code conversion, I am taking the input variable as WXYZ. So now as we know earlier, as a 4-bit BCD number, so it's going to vary from only 0 to 9. Okay, so after 9 it's like from 10 to 15. So it's not a BCD number, so generally we are writing this number with respect to binary form. Okay, so we cannot write a 4-bit BCD number from 9 to 15, only it's varying from 0 to 9. So what I have to do, so find the equivalent XS3 code converter for this BCD number from 0 to 9. For example, first one is 4 zeros. So what is the equivalent XS3 number is? Just add 3 with that. So 0 plus 3, 3. So the equivalent binary number for 3 is 0011. So similarly for 1, the XS3 code value is 40100. Next for 2, it's 5. For 3, so 0110 is called 6. Next for 4, 0100, so it's 7, 0111. Next 0101, so add with 3, so it's called 8. 8 can be represented in terms of 1000. Next 6, 6 plus 3 is 9, so 9 can be represented 1001. Next 7, 7 plus 3 can represent 1010. So as I said earlier, so only BCD number can vary from 0 to 9. As a XS3 number, it can vary from 0 to 15. So that's why we are writing as 7 plus 3 is 10. Then 8 plus 3 is 11. 11 can be represented as 1 0 1 1. Next 9 plus 3 is 12. 1 1 0 we can represent. As I said earlier, we cannot write a BCD number from 10 to 15 as a 4-bit number. So what I have to do, we cannot write a XS3 equivalent for that. So for that outputs, just we are writing as don't care variable as X. So now we completed the truth table. So based on these truth table, so we have to make a K-map simplification. So here we are having a 4-bit variable ABCD as a 4 input variables. So as a 4-bit variable, so we have to use a 16-cell K-map. So by using 16-cell K-map, we can able to find out the simplified answer for WXYZ, I mean XS3 code converter. So we have to get the output for XYZ, simplified answer for WXYZ in terms of input variable ABCD. So first one doing this for W, first K-map for W. So under that, so substitute for 0, it's 0, so no need to represent. So next for 1, it's 0, for 2 it's 0, for 3 0. So the first entire row everything is 0. So just leave as empty, or you can mark as 0, nothing wrong in that. So next for 4 it's 0, 5 is 1, for output for 5 is 1, 6 1, 7 1, 8 1 and 9 1. So from 5 to 9 it's 1, just marked. Then from 10 to 15 for all the output variables, 10 to 15 is don't care, use a don't care from 10 to 15, 10 9 10 11 12 13 14 15. So for that mark as don't care variable. So after marking these variables, now we have to make a grouping here. So obviously we can make maximum cell grouping. First we have to give the importance for maximum cell grouping. So here 8 cell mapping, one 8 cell mapping, octal mapping and 2 quad mapping can be done. So based on that we can able to write the answer for that. So for that 8 cell mapping, octal mapping, the answer is A. Then for the 2 quads we are having answer is BC and BD. So this for the simplified Boolean expression for WXS3 code. Next for doing for X, Y and Z. So for X, yes, based on the previous K-map simplification, we are coming to the logic diagram implementation. So we already calculated the simplified answer for WXYZ with the help of 8 cell K-map simplification. Now implement the logic diagram with respect to that simplified Boolean expression. Now W we know A plus BC plus BD. So 4 input variables are there, A, B, C, D. Then 4 XS3 code converters variables W, X, Y, Z. So implement W, X, Y, Z with respect to the simplified Boolean expression. Next I will see another example, 4-bit binary to gray code converter. So how to convert binary number to gray code number. So same as a 4-bit number, binary number is going to vary from 0 to 15, I mean 4 zeros to 4 1. As a decimal number we call it as 0 to 15. So gray code number also is changing from 0 to 15, we can write it. So now how to convert from binary form to gray form. So what's the way to convert? I mean while converting binary form to gray code converter, so we need to know the XOR gate truth table, XOR gate operation. So once we know the XOR gate operation, so we can able to do. So what's the XOR gate truth table? So when the both inputs are 0 0, output is 0. When the both inputs are 1 1, output is 0. Then other two cases, what's the other two cases? 0 1 and 1 0 case, the output will be 1. So this is the XOR gate truth table. So with respect to this XOR gate truth table, we can able to convert from binary form to gray code form. So for an example, so here the number is given. So like the number is 5-bit number, they give like 0 1 1 0 1 is the given binary number. So how to convert binary number to gray code number? So first digit is called as MSB bit and the last digit is called as LSB bit. So the first MSB bit as usual same, I mean we have to write the same number. Suppose MSB bit is 1, the same MSB bit will be 1 for the gray code number also. So suppose it's 0, same 0 will be there in gray code also. The MSB bit will be always same. So as in the given example, 0 is the MSB, the same 0 will come as the MSB for gray code number. Now for the second digit, so first digit MSB bit XOR of second digit. XOR of second digit means 0 XOR of 1. 0 XOR of 1 is, what is the answer for XOR gate truth table? 0 XOR of 1, the answer will be 1. So the answer is 1. Next one, for third digit, second digit XOR of third digit. So 1 XOR of 1, the answer will be 0. Next, for fourth digit, third digit XOR of fourth digit. So I mean 1 XOR of 0. So the answer will be 1. Next, for a fifth digit, 0 XOR of 1, so the answer will be 1. Okay, so once you know the XOR gate truth table, so we can able to convert from binary form to gray code form easily. So now here we going to design a 4-bit binary number to 4-bit gray code number. So just list out the input variable 4-bit binary number from 0 to 15 as a decimal number. So write the equivalent binary form from 4 zeros to 4 1. Now so we are going to write a equivalent gray code number as per this XOR gate truth table. So now first one for MSB bit, same MSB bit 0. Next for second digit, 0 XOR of 0, obviously 0. Then again 0 XOR of 0 is 0. Then again 0 XOR of 0 is 0. So this is the equivalent gray code for that. Next one for the second variable, 0 XOR of 0, again is 0. Then 0 XOR of 0 is 0. Then 0 XOR of 1 obviously is 1. Next for third one, 0 is the MSB bit, same MSB bit 0 here. Then 0 XOR of 0 is 0. 0 XOR of 1 is 1. Then 1 XOR of 0 is also 1. So similarly you have to fill the truth table for all the variables from 0 to 15. For example, say another number like for this number 14. 1 is the MSB bit, same MSB bit is 1. Next for second digit, 1 XOR of 1 obviously is 0. 1 XOR of 1 again is 0. Then 1 XOR of 0, 1. Okay, so similarly you can able to fill these two table. So after filling the two table, so what we have to do, we have to find out the simplified answer, simplified boolean expression for this variable, gray code variable. So we have to find out the simplified expression for G3, G2, G1, G0 in terms of binary input variable B3, B2, B1, B0. So see the truth table, see the K-map simplification. So this is the equivalent truth table what we discussed in the previous slide. So now substitute this variable in the K-map simplification. 16 cell K-map we have to use it. We are using a 4 variables, so obviously 16 cell K-map. For G0, first one for G0 we are doing map the variable G0 variable. So for 1 it's 1, for 2 it's 1, then for 5, 6, then 9, 10, then 13 and 14. Only these 8 variables are as 1. Just map that value as alone. In K-map you can able to see the green color represented and the orange color represented. These two are the maximum variables. So just mark that variables. After that we can able to group that. So we can able to make it 2 quad of grouping. So from that we can get the answer as like this B0 and B1 bar. Then we can get B1 B0 bar. So what will be the answer? We are getting for G0 B0 B1 bar plus B1 B0 bar. So the answer will be like B0 exclusive or B1. So the simplified form of that one. Next for second one, for G1 we can do it under G1. So map the variables in the K-map cells like for 2, 3, 4, 5, then 10, 11, 12 and 13. So these 8 cells are as maximum variables. Just map that variables alone. So that variables are mapped. Then after the mapping we can able to group it. So 2 quad grouping can be done. So these are the 2 quad grouping here we done. So based on that we can able to write the simplified answer The simplified answer is like B2 B1 bar plus B1 B2 bar. So we can write the simplified one with the help of XOR gate like B1 XOR B2. Then for G2, what are the variables are maximum? We check it here: 4, 5, 6, 7, 8, 9, 10, 11. These 8 variables as maximum variable. So substitute that variables. Then here also we can make it in terms of 2 quads. By making the 2 quads, the answer what you are getting is B2 B3 bar plus B3 B2 bar. So the simplified answer using XOR gate B2 XOR B3. Then the last one G3 we are getting the maximum variable for the decimal number of 8, 9, 10, 11, 12, 13, 14 and 15. So for these 8 variables as maximum variable, so map this in the K map. So after the mapping we can able to do the grouping as a single octal grouping. So the answer will be B3. So we can write G3 should be equal to B3. So now we got the gray code simplified answer for G0, G1, G2, G3 in terms of binary values like B1, B2, B2, B3. So by the simplified answers, we can able to make like logic diagram for that. So the input values are in terms of binary values from B0, B1, B2, B3. Then output values are in terms of gray code number G0, G1, G2, G3. So with respect to that, so basically G0 should be equal to, we can write directly B1 XOR B0. So by using 2 input XOR gate we can get it. So similarly for G1 also B2 XOR of B1. So then for G2 we can write it B2 XOR of B3. Then G3 should be equal to B3, directly you can connect it. So this is a logic diagram for 4-bit binary to gray code conversion. So similarly we can able to do code conversion from one form of code into other form of code. So we discussed about now BCD to XS3 code conversion. So similarly we discussed about binary to gray code conversion. So vice versa we can do like gray code into binary code conversion. So similarly XS3 code conversion into BCD code conversion. Then we are having other code conversion like other ways, BCD to gray, gray to BCD code conversion, then XS3 to gray code conversion, gray code to XS3 code conversion. So these are the different type of form of conversions can be performed under code converters. So this one is not only applicable for 4-bit code conversion, it may be applicable for 8-bit code converters also. So while moving for BCD number, generally as a 4-bit number is varying from 0 to 9. If you are moving for 8-bit number, so obviously we can able to increase 10, 11, 12 and all. So that coming under 8-bit code conversion. So that can be performed. Then after that, this code conversion is mainly applicable for like the examples we can say 7-segment display conversion. How we are converting BCD number to 7-segment display. So that and all possible with the help of code conversion. This code conversion is one of the main example for combinational logic circuit. So whatever the combinational logic circuit we are doing, so we have to get the statement first, then after the statement we have to make a truth table, then after the truth table we have to make a K-map simplification, then from the K-map simplification we can make a logic diagram. So when the number of logic gates are connected together to get us some specified Boolean function with respect to the variation of input combinations, that's coming under combination logic cycle. So here shown for a reverse one, the previous one we discussed about binary to gray code converter. Suppose we are doing reverse model gray to binary code converter. So how to do the conversion? So same while doing binary to gray code conversion we used XOR gate truth table. Same while doing gray code conversion also we need a XOR gate truth table. So the same one, like when the inputs are 0 0, so or when the inputs are 1 1, output is 0. When the input is 0 1 or 1 0, that combination the output will be 1. Same one we are going to use it for grade 2 binary conversion, but the way of process is different. Listen here, for example, the given gray code number is like 10100. It's a 5-bit number. The given gray code number is 10100. So it's a gray code number. Now we have to convert this gray code into binary code form. So the same, first MSB bit as usual, like the same digit, same one, we're going to come the same MSB bit 1. Now for getting the binary second digit, so the output, first digit output XOR of second digit gray code number. So 1 XOR of 0, obviously output will be 1. For third digit, second digit binary output with third digit gray code input. So 1 XOR of 1 again is 0. Next for fourth digit, third digit output XOR of fourth digit input. 0 XOR of 0 is 0. Next for fifth digit, fourth digit output XOR of fifth digit input. So 0 0 again is 0. So the same process. After that what you have to do, so the gray code is listed from 0 to 15 here. Then find out equivalent binary form from 0 to 15. Write the equivalent binary form. Then simplify by using K-map for B3, B2, B1, B0 in terms of G3, G2, G1, G0. Then make a logic diagram for this. So similarly, we can able to perform various type of code converters. Thank you. We'll continue the other type of method in next class.